Any questions?
Oh, when do we get our test back?
Today.
Oh.
They, except for one test, they were graded shortly after you took them. And then I decided, for whatever reason, to carry them back and forth. But no, they are graded, and the grades have been recorded in my spreadsheet. Other questions? A reminder that the homework quiz in chapter 7 is on Wednesday. All right, so let's go to the putty being thrown at a thin beam or thin bar. And I guess I need to about 1.5. And the putty's gonna stick, so it's a perfectly inelastic collision, and the question is, what will be how fast will the beam putty combination spin after the collision? Now, collision, it is on this is an overhead view, so you're looking down at it as the putty comes in, hits it, so I'm not worried about gravitational pull. Gravitational pull would be into the board, and there's normal force coming out, but we're gonna make the surface frictionless, so the normal force is not gonna have an impact. So normally in collision problems, what's conserved?
Momentum.
Yeah. Except now I've got some rotation going on here, so what do you suspect is conserved? I'll ask that again. I think people have caught up writing stuff down.
So what is the diagram of? What's the 0.7 meters?
That's the length of this bar. This is
It's
I have a thin bar or rod sitting on a frictionless table. It is pivoting about that point.
oh,
Check. There we go.
What is
Towards
the,
it, I'm sending a blob here.
What is the 0.1 meter?
That is the distance from the end to the pivot point. And the blob is gonna hit 0.15 meters from the other end. So the question again is, in a normal collision problem, momentum is conserved. However, in a problem where there is rotation going on, what do you suspect is conserved?
Energy?
Energy won't be, they're gonna stick together, so definitely energy will not be conserved. So when you said momentum, I think Stowe, you said it. What did you mean?
Momentum?
What is the formula then?
V equals mv.
Okay. Except, what would you use for V here? Well, okay.
Velocity? Or speed?
After the collision, how would you figure out V?
Take the derivative, so like, would it be omega? No.
If omega's coming into it. We're not talking about just normal momentum. It's an angular problem, angular motion problem. There's rotation going on, or will be once it hits.
Torque. Torque?
Torque's not something that is conserved, just like force is not conserved. Sorry, spoiler here, just to move it on. Angular momentum. Angular momentum is conserved. I mean, normally P is equal to mv, but after the collision, it'd be very difficult to really come up with a velocity, because if nothing else, the speeds are different depending on where you are on the bar. But angular momentum is conserved. So I guess that brings up the question of, what's the formula for angular momentum? So normal momentum, P equals mv. Suddenly it changed colors. Great. That's great. Well, thank you for the electronics. All right, so we have P equals mv. Angular momentum, generally symbolized by L. What is that equal to? And while you're looking that up, let's see if rebooting this will work. We're doing a translation, or
Is it a MW?
not M. I assume you meant omega.
Yeah.
All right, omega, I'll go with angular velocity.
I?
Yeah, there we go. The rotational inertia, or moment of inertia. It seems to be writing again. All right, so I know that my total angular momentum, so L initial, is equal to my total final momentum. Just like with regular momentum, or momentum as we say in the business, is that the total momentum is just the sum of the parts. So this would be L, I'll put B for bar, initial. Actually, let me use R plus L ball, initial. So that's B, that's R, is equal to L R final plus L B final. Or we could actually combine those into L R B final. Since the thing is going to, the ball is going to stick to the rod, it is just one object. All right, so let's figure out what the moment of inertia is, R. So I have I of the rod initial
times omega of the rod initial. Plus I ball initial, omega ball initial, equals IRB final, omega final. So let's start out with the rod. What's the moment of inertia of the rod, or how would you find it?
Is it 1/2? Or no, 1/12? Something like that?
1/12 what? You got the hard part.
ML squared.
Yeah, there we go. As a group, we got it. So I of a rod, that 1/12 ml squared. Because moment of inertia requires some axis of rotation. What axis of rotation is involved for the 1/12 ml squared?
The center.
Yeah. So that's about the center of mass, rotating about a point smack dab in the middle. So how do we deal with it when the moment of inertia is up here? Sorry. How do we deal with it when the axis of rotation is, instead of being here, is here?
You do square.
Dominic, are you about to say something?
Thinking, but it's either gonna be right or it's gonna be completely wrong.
Go for it.
Doesn't it not matter where the axis is?
It matters a great deal, because if,
Okay, yeah.
so moment of inertia, really, it's an infinite sum of mr squared. And so r is the distance from any point on here to where the axis is. So,
That's what we did. That experiment where you were like holding the rod, or not as an experiment, but you were like holding the rod. It's like it's gonna be a little bit to the left, a little bit to the right, and it was like, it ended up not mattering.
if you have something in static equilibrium, it doesn't.
Okay.
Static rotational equilibrium, it does not matter.
Okay.
But this definitely will not be.
The U plus the mass 8 squared.
Yeah, the parallel axis theorem, because we're moving the axis from the center of mass to an axis parallel to that. And so the moment of inertia of the rod will be the moment of inertia of the rod about the center of mass plus m times h squared, where h is how far we moved the axis. So let's take out bit by bit. So we have 1/12 times mass of, I said 1.2 kilograms times a length of 0.7 meters squared. And if someone would be kind enough, oh, excellent. 0.049. You're just gonna trust my doing it in my head. Yes,
Where did the 1/12 come from?
right
Oh,
there.
this is part of the formula?
Yeah.
Okay.
Or I could have also gone with Ryan said so. But it comes from the formula. If Ryan had said something else, he would not have been correct.
It is.
0.049 units?
Kilograms times meters. What can you say?
Yeah,
I heard kilograms times meters.
times meters squared.
Squared, yeah. Don't forget, we are squaring it right here. Kilogram meters squared. All right, well, that is about the center of mass, but we are shifting it, so it becomes 0.049 plus the mass of 1.2 times a distance. How far are we shifting it? If we assume the rod is uniformly, just has uniform mass distribution, in other words, the center of mass is smack dab in the middle.
0.25.
0.25 squared. And we end up with
0.124.
so we know that.
How'd you get the 0.25?
We're shifting the axis, so the center of mass is in the middle. So this distance is 0.35 meters, and we shifted it till it's 0.1 meters from the end. It's just the difference of those two. What's the initial angular velocity of the rod?
0.
So this whole thing is going to be equal to 0 because omega r initial is equal to 0 radians per second. We will, the number that we just calculated over there, we will be using that in a moment. So it wasn't, otherwise I would have gone to that first and just gotten rid of the term. Now we've got the moment of inertia of the ball and the angular velocity of the ball for something that's traveling in a straight line. So the question is, how do we figure out the angular values for something that's traveling in a straight line? I can't just do, oh, let's just use linear momentum, P equals mv, because the units wouldn't work out. Well, if moment of inertia is the sum of all the mr squares, let's first off just assume point mass. What I care about is the ball when it's here, not when it's way over there. So if I just add up all the mr squared, I just have the mass of it times that distance squared. So the moment of inertia of the ball is the, is the mass of the ball times r squared. So that'd be 0.5 times r, which is the distance from here to here. So the whole thing is 7, I'm taking off 0.25, so 0.45 squared.
0.55? Wait, yeah, 0.55. Wait, oh, wait. To
It's
the
point-
thing. Never mind.
Okay. You're good with
To the-
0.45?
Yeah, to the point of the axis.
Okay, what do we get?
Zero point zero three oh three seven.
0.03037?
Yes. Never mind.
That does not strike me as right.
I'm putting an extra
Square.
digit.
Oh.
0.10125.
0.1025?
125.
10125?
Yes.
Now, there is an alternate way of finding that moment of inertia of something traveling in a straight line. And let's just go ahead and do it. If you're talking about an individual particle, like we are here, it's a point mass. The moment of inertia of a point mass is just R across P. If you think about force is R, torque is R cross F, L is R cross P, then actually there's a relationship there. R, well, it's gonna hit, so let's set up a coordinate system here. I hat, J hat, and that forces K hat to come out of Atlas. So R would be a vector from the axis rotation to down here. So that would be 0.45 meters negative J hat. Crossed by momentum, which is mass times velocity, which would be 4 kilogram meters per second, negative I hat. Then those negatives would cancel out, then I'm left with 0.45. We only found I there. 0.45 times 4, J hat cross I hat. So that's gonna be 1.8 J hat cross I hat. What is J hat cross I hat? Assuming a right-handed coordinate system. It is not K hat. It is perpendicular, so